All right. So hello everybody. Oh, nice to have a watch. I will just remind you where we're standing. We are dealing with quantum fluids or gases, and we are dealing with a very simple example of three states. Okay, so our energies were epsilon 3, epsilon 2, and epsilon 1. Okay, and we were dealing with fermions. Okay. Now, the idea was that per state, we also had some sort of a degeneracy of a spin plus 1/2 minus 1/2, okay? But per quantum state, for a given spin, we could have only either one particle or zero particles that are, this is the statistics of the fermions, okay? Eventually, we managed for this simple system to obtain some sort of factorization, but this factorization was very different from the factorization of canonical ensemble. We dealt with grand canonical ensemble for this case. Why grand canonical ensemble? Because the particles, specifically due to this reason that they interact, how they interact when a given state is occupied, no other particle can penetrate to this state. Okay, so what we do have over here, we cannot use canonical ensemble because of these interactions, and we used grand canonical ensemble. Now, the moment we used grand canonical ensemble, we managed to obtain this factorization, but factorization was not for the particles. The factorization was for different states. Okay, eventually we obtained that Z was Z1 multiplied by Z2 multiplied by Z3, okay, when Z1 was the partition function of state 1, Z2 was the partition function of state 2, Z3 was the partition function of state 3, and due to the degeneracy of each state, okay, what is the degeneracy? For each state, we could have two particles either with state with spin minus half, S equals minus 1/2, or S equals 1/2. So that brought another factors or powers of 2 over here. Okay. What is Z1? Okay. What was our Z1? So Z1 was 1. It was 1 plus e to the power minus beta epsilon I minus mu. Okay. This is what we managed to obtain last week. Okay. Where we started to head from this description, we started to ask the question, what is the probability of finding a particle in a given state? Okay? If I'm looking on a given state over here, epsilon 1, what is the probability to find the particle in a specific state? Now, since we have factorization, we don't care what is going on in all the other states. We're only looking on the particle or on this subsystem that includes only the specific state, and we're saying the following thing. F of I, so the probability that state I is occupied, is e to the power minus beta epsilon I minus mu divided by 1 plus e to the power minus beta epsilon I minus mu. Okay. So this is the probability that we have one particle, okay? This is the prefactor divided by Zi. This result holds for any particles whatsoever, and it's interesting because due to the properties of the statistics, okay, what's the statistics? Either one particle or 0 particles, the average number of particles per state I is what? Is 0 multiplied by 1 divided by Zi plus 1 multiplied by e to the power minus beta epsilon I minus mu divided by Zi. Okay? Or overall, we're getting that Ni average is simply e to the power minus beta epsilon I minus mu divided by 1 plus e to the power minus beta epsilon I minus mu. Okay. Now, the average number of particles for a given state is exactly the probability for the state to be occupied. Okay? So this average is sometimes called occupation probability. Now, we can write it down a little bit in a different fashion. So first of all, it equals to Fi, right? And we actually can take this from the numerator into the denominator and obtain the following formula. It's 1 over e to the power beta epsilon I minus mu plus 1. Nothing courageous. So if you want to study the properties, occupation properties of a given state for our simple model, we need to study the properties of this function over here. Okay. Which we also can write it down as 1 over e of mu divided by k Boltzmann t, epsilon I divided by mu minus 1 plus 1. So this is the function. And let's us write it down as a function of epsilon divided by mu for different mu's. So this is our Fi. This is epsilon I divided by mu. Okay. And I want to plot it for different values of mu. So first of all, if mu is something like 1k Boltzmann t, okay? So when this value over here, let's write it down, Fi equals to 1 over e to the power mu by k Boltzmann t, epsilon I divided by mu minus 1 plus 1. Okay, this is the function that we are plotting. When mu divided by k Boltzmann t is of order 1, okay, and when epsilon I divided by mu is going to 0, so we're starting not from 1, we're starting from some number which is exactly equals to 1 over e to the power minus 1 plus 1. Okay, so it's somehow lower than 1, and this is our starting point. Okay. Eventually we will start and we will decay towards 0. Why we will decay towards 0? Because when epsilon divided by mu goes to infinity, we have 1 over e to some very large number plus 1. Plus 1 is not important, so it's 1 over something that goes to infinity, so it actually converges to 0. An interesting point is the point where epsilon divided by mu equals exactly to 1/2. Okay? 1, I'm sorry, not 1/2. 1. Why it's interesting? Because when epsilon divided by mu equals to 1, we have 1 divided by, here we have e to the power 0, which is 1 plus 1, so this guy is exactly 1/2. Okay? So this plot is for mu equals to k Boltzmann t. Now we can start and raise cube K Boltzmann T. We can take mu equals not K Boltzmann T. Mu is the chemical potential. It has units of energy, okay, joules actually. So we can raise it up and we will go to something like 5 or 10 K Boltzmann T. Then we will start with a value which is much more closer to 1, okay, when epsilon divided by mu equals 0. So it is e to the power 5 or minus 5 plus 1. Okay, so it's almost 1. Okay. We know that when epsilon divided by mu equals 1, it has to cross this point. Okay, so it goes to something like this. And eventually, when epsilon divided by mu grows up to infinity, Fi decays towards 0. Okay, so what we see, we increased our chemical potential, and the function became much more, it looks at least, much more like a step function, right? It is almost constant over here, it decays towards 0, and we have some transition region, okay? What it actually means, it actually means for when the energies are very small, and the chemical potential is pretty big as compared to K Boltzmann T, the probability of the state to be occupied is almost 1. When the energy is very large, okay, as compared to what? As compared to the chemical potential, okay, then, I'm sorry, then the probability to actually occupy the state becomes very, very small. It converges to 0. So you see, it's according to the temperature and according to the chemical potential of the system, I have some sort of a transition from probability to for sure or almost for sure occupy the given state, or the probability or 0 probability for the state to be occupied. Okay? When we increase our chemical potential even further, okay, we'll start from 1 or almost 1. It has to cross this line over here. And it has to decay very fast towards 0. So this is something like mu equals 5 K Boltzmann T. This is mu equals 30 K Boltzmann T. Okay? So here we already observe a step function for the probability. The energy is smaller than mu, okay? The probability is 1. The energy is larger than mu, the probability is 0. So we're looking on a system, or we're looking on a state, and we managed to perform some sort of a factorization over here. Again, we're saying that, asking the following question: is this state going to be occupied, yes or no? Okay? And the only thing that matters when either the mu is very, very large, or what is important is not actually mu. What is important is mu divided by K Boltzmann T. Mu divided by K Boltzmann T. When mu divided by K Boltzmann T goes to infinity, okay, so either we have very, very, very large mu, or either we have very small temperature, we obtain this transition step function from 1 up till mu and 0 afterwards. So all the states with energy that are lower than mu are going to be occupied. All the states that are higher than mu, okay, are going to be what? Completely empty. Statistically, this is the probability. If the probability here is e to the minus 2000, okay, we won't ever see any electrons in this state, or particles. Right, so what's important is this mu, or more specifically mu divided by K Boltzmann T. Now, since mu determines this probability, or this transition from occupation probability of 1 to occupation probability to 0. It has a very special name. Mu is Fermi energy. Okay. What does Fermi energy means? It means that we have a specific energy in a system, okay, that for low temperatures, or when this Fermi energy is very, very, very high, for all the states below this energy are going to be occupied, and all the states above this energy are not going to be occupied, okay, when the temperature is 0. When the temperature is not exactly 0 and we have some sort of a much more smoother transition, like for example this blue line over here, what actually happens? There are only specific states with very specific energies that contribute to the behavior of the material. Why? If my energy is very small and I'm somewhere over here, this energy is definitely occupied, this energy. This energy is also definitely occupied. This energy is also definitely occupied. This energy is also definitely occupied. So we have a range of small energies that they are all occupied. Okay? When there is a probability which is not exactly 1 to be occupied, in some region, okay? In some region around this Fermi energy, around when epsilon divided by mu equals 1. So in this region over here, the occupation probability changes from 1 to 0. What it actually means, so if I look one time, it's going to be occupied. I'll check again, maybe it's not going to be occupied. What does this mean? This means there is some sort of a dynamics. Particles are entering the states and getting out of the states as a function of time. Okay? So only those states are going to contribute, eventually we will see this in examples, for fermionic systems, they are going to contribute to the behavior of the system. Because all the other states with very small energies are constantly occupied. So they're not contributing anything. It's like I have a lot of boxes. Some of the boxes are always full. I don't care about the full boxes. The only thing that matters is the amount of boxes that are sometimes full and sometimes empty. Where are those boxes? Boxes with extremely high energy are not important, but because they are never occupied. Boxes with very small energy are also unimportant because they are always occupied. So I have some sort of a range, energetic range, for some states that are sometimes occupied, sometimes not occupied. And only those states are going to contribute to my behavior. How do I find it? Any questions about this? Oh. So how do I find this mu? You see, I have a very given specific mu over here, this Fermi energy. I have to find it somehow, have to determine it. Because only energies that are near this mu are going to contribute something to my behavior. How do I define this mu or find this mu in general? And actually, pretty hard to find what is the Fermi energy of a given system. Okay? Sometimes there are ways, actually, for very simple and specific systems. Let's see what happens for our system where we have 3 states. Okay? Where we have 3 states. How from this energy we can obtain what exactly is mu. Okay? Now remember, for grand canonical ensemble, what is constant is T and mu. Those quantities, the temperature of the chemical potential is constant. Now, what we can do, we can change the temperature and we can change the chemical potential. And it will dictate what is the distribution functions, what are the different probabilities to be in a very specific states. Okay, those guys are also determine what is the average number of particles in my system. You see, for this system, the average number of particles is not constant. I cannot say I have 3 particles. If I have constantly 3 particles, I couldn't solve it. I managed to solve it when I said, well, I have random number of particles. Okay, this is why I could sometimes say, well, maybe there is 0 particles at this state, maybe there is 1 particle at this state. Okay, so my general number of particles is not constant. What is constant? The average number of particles is constant for a given t and given mu. Okay? Now, any physical system, let's assume that I have, eventually we will try to see what happens in electronic systems. A system with conducting electrons. Okay, the number of electrons that are eventually I'm looking on in the system, on average, is constant. If I don't have big evaporation or I don't have some loose ends, the number of particles, the average number of particles is constant, and sometimes it's independent of the temperature. Okay, so I want to determine mu, or at least I think I can determine mu, for a system where I say the average n is constant and it's independent of the temperature. Okay, by using this property of constant average number of particles, okay, I can determine my mu over here by using average n and t. Okay, so what I'm actually saying is that t and mu, I should give it to you. I can actually say, well, I can determine t if I determine n and determine t. Let's see how it works. So for this system, average n is what? Is the average number of particles that is sitting in this state, okay, which was 1 divided by 1 plus e to the power minus, beta epsilon minus mu, epsilon 1 minus mu, plus the average number of particles that are sitting in this state. Okay, so energy epsilon 1 and spin, instead of minus 1/2, spin 1/2. Now this number is exactly that number, so the only thing that I need to do is to add a prefactor of 2. Okay, what is the average number of particles that are sitting with energy epsilon 2 and spin minus 1/2? So it is plus 1 divided by 1 plus e to the power beta epsilon 2 minus mu. And again, I have particles state degeneracy for spin minus 1/2 and spin 1/2. So I again put 2 over here. Okay, and I have the third state. Now here again, I have this degeneracy of spin minus 1/2, spin 1/2. It does not determine the energy, which is always epsilon 3. Okay, so here I again have 2 multiplied by 1 plus e to the power beta epsilon 3 minus mu. Okay. Now instead of beta, we can write simply 1 over k Boltzmann T, 1 over k Boltzmann T, 1 over k Boltzmann T, 1 over k Boltzmann T. So what is my claim? This is always holds, no matter what mu is, no matter what the temperature is. Okay, this is my statistics. This is the property, or this equation over here I obtain for any t, okay, and any mu, and this guy should always hold. Now I can say the following. Let's assume that we're looking on the system that the average number of particles is constant, okay, and it should be independent of the temperature. Okay, so n is constant, right? T, I have a control over t, and since I have constant n, this is my parameter, t is my parameter. Out of this ugly equation, I can determine what is mu. Okay, so how I determine what is mu? I have to solve this equation and find mu equals to what? All right? So this is what we have to do, and you already see that actually this is an unsolvable question even for this simple system of 3 states, 6 state. I cannot solve this easily. What I can do in order at least to try and do something, or at least present to you how it's done, I can assume some simplicity. I'm saying let's 3 states is an overkill. Let's assume that epsilon 2 and epsilon 1 are exactly the same. So basically I have, instead of system with 3 energies, I have a system with 2 energies. The degeneracy of epsilon 3 is 2, and the degeneracy of this guy over here is 4. Okay? So instead of solving this question, I'm solving this system. N equals to 4 divided by 1 plus e to the power 1 over k Boltzmann t epsilon 1 minus mu plus 2 divided by 1 over e to the power 1 over k Boltzmann t epsilon 3 minus mu. Okay. Okay, so let's first of all let's look on the system which is 1 over e k Boltzmann t epsilon minus mu. Okay? And I want to obtain an approximate behavior of this guy and the limit when t goes to 0. Okay? Because I'm saying at least let's find the Fermi energy, okay, or Fermi level it's sometimes called, for this limit of very small temperatures. Why it's mostly important over there? Because definitely for small temperatures, everything up to the Fermi energy is occupied, everything above the Fermi energy is unoccupied. Okay, now here when t goes to 0, okay, it's somehow reminds me your last quiz. When t goes to 0, I have 2 options, right? One option is epsilon larger than mu, and the other option is epsilon is smaller than mu. Okay? When epsilon is larger than mu, okay, t goes to 0, epsilon is larger than mu, this guy, okay, is positive, divided by something that goes to 0, so that it's exponent of a very big number, positive number. It's definitely larger than 1. We don't care about this one. So it's approximately e to the power minus 1 over k Boltzmann t of epsilon minus mu. Okay? So this is the case when epsilon greater than mu. The other case is when epsilon is smaller than mu. What happens when epsilon is smaller than mu? When epsilon is smaller than mu, this guy is negative, divided by a very small number, so this guy on total is very, very, very large and negative. Then exponent of a very, very large and negative number is very small. So we have 1 divided by 1 plus a small number. Okay, so what is a Taylor expansion of 1 over 1 plus x when x goes to 0? It is approximately 1 minus x or 1 plus x. So make a guess. Minus. Why minus? Because it's always x is, let's assume that x is positive and very small. So this is 1 divided by something which is larger than 1. So it has to be 1 minus x. Okay, so this approximately is 1 minus e to the power 1 over k Boltzmann t epsilon minus mu. Okay. Now we're working in the limit of t goes to 0, and we want to compute mu in the limit of t goes to 0. Okay, so we're going to have something, okay, or to use this limit for this expression and that expression. Now we have to make a guess, some sort of a guess, if epsilon 1 is greater than mu and if epsilon 3 is greater or smaller than mu. Okay, But this guess is actually pretty easy. Why it's easy? Remember this plot over there. Okay? If the temperature is very, very, very low, and we have only two energies, okay? And we have only two energies, okay? We have epsilon 1 and we have epsilon 3. Okay? Which state is going to be occupied? Epsilon 1 or epsilon 3? Epsilon 1 should be occupied because it has a smaller energy. Now, mu, this Fermi energy according to this plot, it lies somewhere in between where the state is definitely occupied to a situation when the state is definitely unoccupied. So we do expect that mu in this limit of small temperatures, mu is somewhere which is larger than epsilon 1 and smaller than epsilon 3. Okay? This is our assumption. Now, if this is true, we can use this expansion over here for this average n and state the following. Average n equals approximately to 4. Now here epsilon 1 is smaller than mu, then we are using this expression over here. So it's 1 minus e to the power 1 over k Boltzmann T epsilon minus mu. Okay? This is this guy. Okay? Also we have plus 2. And here we need to expand this 1 over 1 plus e to the power 1 over k Boltzmann T epsilon 3 minus mu. Okay? So we're using this expression over here, which is e to the power minus 1 over k Boltzmann T epsilon minus mu. Okay? Now this is already somewhat easier. Why it's easier? Because we have this n, okay? We have this 4, we have 2, okay? So let us transfer this guy into this part. So we have n minus 4 plus 4 e to the power 1 over k Boltzmann T epsilon 1, and this is epsilon 3. Epsilon 1 minus mu equals to 2 to the power minus 1 over k Boltzmann T epsilon 3 minus mu. Okay? What is my next step in order to solve this equation? The answer is there is no next step, okay? Because even this equation is unsolvable. I cannot solve this. There are some mathematical names for these equations, etc., etc. You cannot really solve this. The only instant when you actually can do something and solve this equation, it's only when you are saying, well, let's solve it for a very specific case. What the specific case is? When this equals 0. Why? Because I can solve it. Okay? That's it. I cannot solve it if I had an average number of particles 3.5. I don't know how to solve this equation where I have 0.5 plus 4 multiplied by exponential of something equals to 2 exponential minus something. I don't know how to solve it, and nobody can. I can maybe graphically solve it, but you know, I can solve it numerically, graphically for each given n, but I don't want to do it. I want to just to show to you that it sometimes can be done. Okay? So let's look on a very specific case when the average number of particles for this system is 4. Okay? What happens then? This is an example of a limit of a physical thought, or the limit of mathematics. So when we have this guy, we have 4 e to the power 1 over k Boltzmann T epsilon 1 minus mu equals to 2 to the power minus 1 over k Boltzmann T epsilon 3 minus mu. Okay? We can do this trick. We can take a log out of both sides, and we have log 2 plus 1 over k Boltzmann T, epsilon 1 minus mu, equals to minus 1 over k Boltzmann T, epsilon 3 minus mu. Okay? Alright, so let's move all the mu's to the right hand side and all the epsilons to the left hand side. We're getting 1 over k Boltzmann T of, right, of 2 mu, okay, on the right hand side. On the left hand side we're getting log of 2, okay, and here we're getting plus 1 over k Boltzmann T, epsilon 1 plus epsilon 3. Okay? So from this guy we obtain that mu equals to epsilon 1 plus epsilon 3 divided by 2, okay, plus 1/2 log, or 1/2 log of 2 k Boltzmann T. Okay. So the exact prefactor are not really important. What is important? That this Fermi energy is exactly in the middle of the two states. Okay. Now let's think what actually we have. We have epsilon 1 and we have epsilon 3. Okay. The degeneracy of epsilon 1 is 4. So there are actually 1, 2, 3, 4 different states with epsilon 1. And there are only 2 states with epsilon 3. When I plot the occupation, okay, or any state, f of epsilon I, okay, of epsilon divided by mu, I'm having that when t goes to 0, I will have a transition of 1 and 0. Okay? Here is epsilon divided by mu equals exactly 1. Now, in our case, mu is somewhere in between epsilon 1 and epsilon 3. Where exactly it is located? It's located for temperature, for t goes to 0, we don't have this prefactor, so it's exactly in the middle. This is our mu. Mu equals epsilon 1 plus epsilon 3 divided by 2. What happens as we increase our temperature? So what should happen to the occupation fraction? Occupation probability. This occupation probability, instead of being a step function, okay, for temperatures that are getting higher and higher, it starts to be smoother transition. Okay? What it actually means? It actually means that this Fermi level, Fermi energy, is getting away from epsilon 1 and much more closer to epsilon 3, thus increasing the occupation probability of the higher level. For a very small temperature, for a fermionic system, okay, and we have on average 4 particles, on average, all the 4 states with the lowest energy are going to be occupied. Okay? Here we have a gap between epsilon 1 and epsilon 3. So anything below this mu is going to be occupied. Anything above this mu is not going to be occupied. Okay? As temperature grows, the occupation probability becomes smoother than a step function. And we see this effect by noticing that the Fermi level is getting away from the lowest energies and towards the higher energies. And this expression, although we obtained it for a very specific average n, okay, one can always say that mu is sitting somewhere between all the states. If you push all the average number of particles to those states, it sits just above the state that its mass has to be occupied with all the particles. Okay? Then there is a gap between this highest state, which is epsilon 1, and the next state. What happens as we increase the temperature? This Fermi energy is going towards higher and higher and higher energies, and usually the dependence with the temperature is linear as we see it over here. Okay? So although it is a very simple example, and for this simple example we can calculate what is the Fermi energy is, generally we can't. Why? Because remember this. Even here we had to push inside all the possible simplifications that we can in order to solve this nonlinear equation, and it's usually unsolvable. So the Fermi energy depends on the average number of particles. It depends on the temperature. Okay? It's somewhere in between the lowest possible energy and the slightly higher energy. Okay? And it's growing with temperature as we increase the temperature. That's it. Exactly what this Fermi energy is, we usually don't know. All right. Now another thing to notice about the Fermi energy is, I already told you about it, but the only thing that matters is this transition region. Okay, why? We're going to see it in the next example. All the particles or all the states that are constantly occupied are not important. All the states that are constantly unoccupied are not important. The only importance is in the vicinity of this energy, the Fermi energy. Okay? Why it's important? If you look on the expression of f of epsilon, okay, it is always in this following form: 1 over 1 plus e to the power mu divided by beta, okay? I'm sorry, mu k Boltzmann T, epsilon by mu minus 1. Exactly when epsilon equals mu, okay, when our state is at the Fermi energy, this is 1/2. Now, because of the form that we have over here, we have an exponential fast decay towards 1, or this function approaching exponentially fast with energy towards 1, and it's exponentially approaching 0, okay, on this side. This length over here, okay, how fast I'm approaching either 1 or either 0 is always given to us by what? By k Boltzmann T. So we're looking on some region which is determined by mu divided by k Boltzmann T, okay, which is divided by, or e to the power mu divided by k Boltzmann T. It is the decay rate of this function towards 0, and it's the approaching rate of this function towards 1. Okay. So we can say that mu divided by k Boltzmann T, or mu divided by k Boltzmann T, somehow describes to us the region, sorry, it's not like that, this decay and this decay over here describes to us the region where we actually can operate on the system, where something can happen. Any other values of the energy are completely unimportant because nothing really happens over there. Let's see this in the following example of electron gas. So this is a model of a system, or a box, we can say, that contains a lot of electrons, and all of them are free electrons, and all of them, this is the name gas, are completely non-interacting. Okay? Now we want to find the property of the system, and as I mentioned, the system is just, we have huge number of electrons, they're all located in a box, okay? They're all fermions, and we want to obtain some properties or thermodynamic properties of the system. Why it's important? Free energies in some box. This is actually a very good model, as we will see, for electrons or behavior of electrons in metals. Okay? Actually, when we're using properties of conduction electrons, okay, for how electrons are streaming inside coils or inside metals, we're using a description of a system which is exactly free electrons in a box. Now we will see why this very simple thing is actually working, because one can assume, wait a second, electrons are interacting with each other somehow. They're interacting with the material, they're interacting with each other. They are not free. Okay? They're definitely fermions, so they have to interact due to the quantum properties, but they're also not free. They have charges, they have some sort of Coulomb interactions between them. How one can assume that I'm having, or I'm looking on the system of completely free energy, free electrons that are not interacting. We will see that this is actually extremely good solution of any system with huge number of electrons. Okay. So what is the deal over here? We have many energies or many electrons. All the electrons are free. So the energies are dictated by the k number of each electrons and are simply provided to us of p squared divided by 2m. All the electrons are free, so there is only kinetic energy for each electron, okay? And if we're using that p equals h bar k, so the energy of a given, it's not an electron or a given state, it's important to remember that we are dealing with states over here, is simply h bar k squared divided by 2m. And we can put an me over here because this is the mass of an electron. So our system, we have a lot of electrons inside the box. I don't know how they look, right? I don't know how they behave. I assume that they are free electrons. I assume that they are quantum particles. I assume that they have Fermi statistics, or basically they cannot occupy exactly the same state, right? And I need to obtain some thermodynamical properties of the system. Okay? I want to understand what is the average energy of the system, what is the average number of particles in the system. I don't really know. How I solve it? Okay? Since we're already using a grand canonical ensemble, this is the same way we're going to approach this electron gas. Now, there are properties that we completely neglect. We neglect interaction, okay, Coulomb interaction, for example, between different particles. Okay? But we do not neglect their quantum properties. What this means? This means that it is forbidden for two electrons to be exactly in the same state. Okay? Now then, this is somehow reminds to us this problem that we just solved. There we had three energies, okay? Three energies, and for those three energies, we managed to obtain some sort of factorization. But factorization was not for particles, but for states. Exactly the same happens over here. I would say, look, what is the partition function? Because any thermodynamical or statistical mechanical calculation in our class starts and ends with what is the partition function of the system. Okay? So the partition function of the system is a sum over EI, right, minus mu and I. Okay? I have to go over all possible state. I have to calculate the energy of a given state, but the state is also provided to me not just by what is the energy of the state, but also what is the average number of particles in this state. Okay? Sorry? Oh, yeah, sure. Minus beta. Okay? I cannot claim that beta is minus 1. All right. Now, what we have done for the three states, okay? We said, well, the energy, the total energy, okay? The total energy is the energy of all the states that are occupied, okay? And N and I are what? Is the total number of occupied states, okay? So when we're looking on this, we can say it is actually a multiplication of all the different states, that it's minus beta. K now is our states that are provided to us by those energies, okay? E to the power beta nk epsilon k minus mu. What is nk? Nk equals either 0 or 1, okay? It equals 0 when unoccupied, and it's 1 when it's occupied. The transition from this line to that line is similar to the transition that we've done on our last lecture. So what exactly we have done? We said, what is this energy? The total energy. The total energy in a given state I is a sum over k nk epsilon k. If a state is occupied, it contributes to the total energy. If the state is unoccupied, it is not contributing to the total energy. What is the number of particles for a given state? It's again a sum of k and k, right? If a state is occupied, there is one particle. If the state is non-occupied, there is no contribution of this state to the total number of particles. Okay? Now, we can write down this as a sum and this guy as a sum. And instead of saying what is epsilon I minus mu n I, we can say that this is a sum, okay, over all different k's of nk multiplied by ek minus mu. Okay? But all the different nks are independent of each other. It doesn't matter if state 3 is occupied. It does not contribute. It does not contribute to occupation or unoccupation of state number 4 or 5. They're independent of each other. So those n's over here are independent. This is why I can go from this line to that line. Here I have a summation. Here I have a multiplication of what? Of a summation of all of the different nks. Nk can be either 0 or 1. The multiplication comes from the fact that all the nks are independent of each other. Okay? Now, this sum I can calculate pretty easily what it is. So it's pi over k of 1 plus y1 when nk equals 0. I have e to the power minus beta multiplied by 0, multiplied by something. I don't really care what the something is. It's simply 1. Plus e to the power minus beta epsilon k minus mu. This is Z, the partition function of an electron gas or Fermi gas. There are different names for that. Okay? So basically, I obtained again this factorization. But now I don't have only 3 states. I have many states. And the factorization is not on the different particles. Okay? the factorization is for different states, right? So I have a z, the total partition function, is a multiplication of many different partition functions when each partition function is describing to me one given state with a very specific energy, okay? And if I will consider spin, I will also take a spin into account, what's going to happen? So each state is going to be contributing this for spin 1/2, and exactly the same partition function, okay, when it have a spin minus 1/2. So I will have a 2 over here, power 2. This comes from the degeneracy of the different states. Okay, because the energy, I don't have a magnetic field over here, so the energy is independent of the spin. That's it. Now, the moment I have a partition function, and more importantly, when I have a factorization for my partition function, I can calculate anything that I want. Absolutely anything. Okay? I can calculate the average energy. I can calculate the average number of particles of the system. I can calculate the Fermi energy afterwards. Okay? All the different properties of the system are calculable the moment I have this guy. Okay? Now there is one slight problem. How to perform this multiplication over here? The energies are not discrete. Previously I had 3 discrete energies. Now the energies are continuous because those k's are continuous. Okay? So what we are going to do, we're looking on particles in the box. We are going to use what? This density of states. Okay? The same way as we use density of states for the Debye model, or the same way as we use density of states for the black body radiation model, in order to compute this multiplication or compute the summation, we need to introduce how dense the different energetic states are together. Are they sparse? Are they dense? I don't really know. Now this is why I'm using particles in a box, because we already calculate the density of states for free particles or for waves, standing waves, inside a box. Now if I have an electron, I can always describe it as some sort of a wave inside a box. Now before going there, I just want to remind you, if I want to ask the following question: what is the probability that an electron, or it's not an electron, energy, a specific energy, epsilon k, is occupied? Basically asking, what is the probability that I have an electron, okay, with a given energy, epsilon k? Okay, what is the probability? Remember, each state is either occupied or unoccupied. The probability of a state to be occupied, okay, Fk, the probability of state with energy k to be occupied is this prefactor, e to the power minus beta epsilon k minus mu, divided by the partition function of this state. What is the partition function of the state? This is a multiplication over all the different partition functions. 1 plus e to the power minus beta epsilon k minus mu is the partition function of a given state, or with a given energy. So it's simply 1 plus e to the power minus beta epsilon k minus mu. It equals to 1 over 1 plus e to the beta epsilon k minus mu. Exactly the same partition function that we explored previously for this 3-state system. And for any fermionic systems, we always are going to get this distribution over here, okay? This probability. It doesn't really matter how many states we have. It doesn't matter if they're continuous or not. Okay? For each given state, this formula is correct, this probability. Why? Because it's either that the probability that the particle is unoccupied, okay, or the probability that the particle is occupied, and we have to normalize it by the sum 1 plus this prefactor over here. Okay? And it doesn't matter if we have many energies, one energy, because we have factorization. So the probability for a given state or for a given energy to be occupied for fermionic systems is always provided to us by this formula. We need to know the temperature, we need to know the energy, and we need to know the chemical potential. And we always can assume that, well, if the temperatures are really, really low, it's only important if the energy is above the Fermi energy or below the Fermi energy. Okay? I don't really care about all the other states. I have factorization. The only thing that it matters to me in the regime of low temperatures is my energy below or above the Fermi level. All right, so if I want to compute, for example, the grand canonical potential. The grand canonical potential, it's easy. So psi equals -1 over beta log of z. Okay? So it equals to -1 over beta sum over k, a log of multiplication over k over 1 plus e to the power minus beta epsilon k minus mu, all of this to the power 2, which equals to minus 2 divided by beta summation over k 1 plus e to the power minus beta epsilon k minus mu. Okay. The moment I have grand canonical potential, all the different derivatives of this grand canonical potential can provide to me what? The entropy, the energy, the average number of particles. If I have pressure inside the system, the pressure, anything that is determined by those energies over here. Log, right. You're absolutely right. Minus 2 divided by beta, sum over k, log of this. Okay. Now, in our case, the energies are continuous. Okay. So what do we do when we have continuous energies? We're saying the following thing. Instead of having this sum over here, we're going to have an integration. Okay. So the grand canonical potential is minus 2 divided by beta, integration of all the possible energies that we have in a system. Okay. So it's from 0 to infinity, of a log of 1 plus e to the power minus beta epsilon minus mu d epsilon. Okay? And this is the density of states. This is the density of states for any given energy. Okay. How we determine this d of epsilon? Okay, so remember, we did determine d of, not of epsilon, we determined d of omega, right? What was d of omega? D of omega was the volume of our box divided by 2 pi squared, k squared of omega, dk d omega, right? Yep. Now, what we're going to use this expression over here. Epsilon k equals to h bar k squared divided by 2m. So k equals to 2m epsilon divided by h bar square root divided by h bar. Right? So instead of using this guy, okay, we're going to use k which is determined by epsilon, okay? And we also know that h bar omega is epsilon, okay? So we're only changing our coordinates over here. Instead of using omega, we're changing it into epsilon, from omega to epsilon, okay? And we want to look on what is k squared of omega, okay? We can say, well, k squared of epsilon, it's actually very easy. It's 1, right? 1 over h bar squared, okay? 2m epsilon, okay? So eventually we need to stick everything inside. So what we get? So we get v divided by 2 pi squared. K squared is 1 over h bar squared multiplied by 2 m epsilon, okay? We have dk 2d omega, okay? How we compute this guy? So if h bar omega equals epsilon, k equals 1 over h squared square root 2m h bar omega, okay? We contribute also this guy inside. So dk to d omega is 1 over h bar square root of 2m h bar multiplied by 1/2 square root of omega, okay? And the square root of omega turns into what? It turns into a square root of 2m divided by epsilon, right? Divided by epsilon multiplied by what? Multiplied by 1/2. So what we have over there eventually we have that d of epsilon equals to, so we have epsilon over here, we have 1 over square root of epsilon over there, so it is epsilon to 1/2. We have v, right, divided by 4 pi squared h bar squared, okay? And we also have 2m to the power 3/2. Okay? So what we have eventually is that psi equals to minus 2 divided by beta. Instead of this, so we have an integration from 0 to infinity of, here we have a log of 1 plus e to the power minus beta minus mu. Okay, and here we will put epsilon to 1/2 d epsilon. Okay, and all of these transitions over here eventually brings us to, so we have V divided by 4 pi squared. And here we have 2m divided by h bar to 3/2 integration from 0 to infinity. Epsilon over here.
No, but the other one.
Oh. Yep. So we can get rid of this. And it sounds okay. Now, the moment we have this grand canonical potential, one can take a derivative of this with respect to temperature. One can take the derivative of this with respect to chemical potential, with respect to pressure. With whatever you like, you can take the derivatives, and then you will obtain your answer. The more natural way to do it is actually not by calculating this this grand canonical potential. Not because, you know, some other way is more comfortable. Eventually, we will have to solve those nasty integrals over here. There is no way to escape from this, okay? But we can actually do a little bit better by using our physical and mathematical intuition. For example, if we want to compute the average number of particles, okay? So the one way, as I mentioned, is to take this grand canonical potential and take the derivative with respect to the chemical potential with mu, and as we have seen, it will give us something that is related to the average number of particles. Or we can say the following thing. The average number of particles, n, okay, is a sum over k, the average number of particles for each energy k. Okay? What is nk? This formula simply states the average number of particles is the average number of particles of the first energy, of the second energy, of the third energy. They are completely independent of each other, so it's just a sum. The average number of particles for a given energy is, there can be only 0 particles or 1 particle. So it is 0 multiplied by 1 divided by 1 plus e to the power minus beta epsilon k minus mu. Okay, this is our zk. Plus 1 when this energy is occupied, multiplied by e to the power minus beta epsilon k minus mu divided by 1 plus e to the power minus beta epsilon k minus mu. And we obtain that is simply 1 over 1 plus e to the power beta epsilon k minus mu. Okay? So the average number of particles for a given state is simply the probability of this state to be occupied. Okay? Now it's actually very easy to compute what is n. Okay, we don't need to take any derivatives. We don't need anything. We eventually will have some nasty integrals, but it's because the system is continuous. Okay, so what is average n? Is simply average of k, nk, sum over k of 1 over 1 plus e to the power beta epsilon k minus mu. Now, this summation we have to change to what? To integration over all possible energies. Okay, so it is simply 1 plus e to the power beta epsilon minus mu d epsilon d epsilon. Now this d epsilon we already calculated. Okay. So what is it is actually equals to? It equals to v divided by 2 pi squared 2m divided by h bar to the 3/2. Okay, so this prefactor over here. And inside what we have, an integration from 0 to infinity of epsilon to the power 1/2 divided by 1 plus e to the power beta epsilon minus mu d epsilon. Okay. This is the average number of particles in our system. Do we know how to calculate this guy? It seems not that difficult, but it's actually well nefesh. Yep. It's not a nice integral. When it becomes extremely nice integral, in what limit? T goes to 0. Why? Look on this guy. We actually have 1 divided by 1 plus e to the power beta epsilon minus mu. So this is this occupation probability. Do you remember how this guy looks like when t goes to 0? It's a step function. Okay? So this guy, simply f of k. Okay? F of k. It is what? If we write it down as epsilon divided by mu, it starts from 1, okay, when t goes to 0, starts to 1, up to epsilon divided by mu equals 1, and it's 0 for all epsilon divided by mu, for all epsilon divided by mu. Okay? Then, this is very easy. So we look on this integral and we're saying, well, in the limit when t goes to 0, the only thing that I have, this is a step function. The step function means I have to integrate only in the range when this step function equals 1, and that's it. What is the range of integration then? 0 to mu, right? 0 to mu. So it's still 1 when epsilon equals mu. Okay? So this integration is from 0 to mu. Here we have v divided by 2 pi squared, this prefactor of 2m h bar 3/2 epsilon to 1/2 d epsilon. This is already easy, right? So this is simply what? V divided by 2 pi squared 2m divided by h bar 3/2 multiplied by 3/2 mu to the power, 2/3 mu to the power 3/2. Okay? So in the limit when t goes to 0, in the limit of very small temperatures, the average number of particles is what? Is v divided by 2 pi squared 2m h bar 3/2 2/3 mu to 3/2. Now remember what we've done with the system of 3 states? We said we don't know what mu is, because when I plot it over here, or I'm saying, well, the average number of particles determined by the temperature. Okay, here the temperature goes to 0, so we forgot about it. The temperature is almost 0. And it's determined by what? By mu, by the chemical potential. But I want it the other way around, right? I'm looking on a system of electrons. I have an electrons in some metallic rod or a metallic box, and I am saying, well, the average number of electrons is known, and it's constant. What is really not known is mu. This is some sort of an internal energy of the system. Okay? I don't know the microscopic energy. I know that I have huge number of electrons, and I know that they are almost constant all the time, at least for this range of temperatures. Okay? So I'm doing the other way around. I know now the connection between n and average n. Remember, it was very difficult for three energies. It's very easy when your energies are continuous. Okay? At least in this range of t goes to 0. So I can obtain mu, given I have a very specific average number of particles. So mu equals to what? So it equals to 3n multiplied by pi squared divided by v, okay, multiplied by, so all of this to the power of 3/2 multiplied by 2m divided, I'm sorry, h bar divided by 2m, right? No, I've taken, no, it's okay. Why it's 2/3? I have, no, it's fine. Well, mu was to the power of 3/2. All right, so I transferred everything to the left-hand side, okay, and I've taken the 2/3 power, okay, or 3/2 power of both sides, right? I need to cancel 2 and 3. No? No. Wait. So mu was 3/2, so it's 2/3. I'm the silly one over here, and here we have nothing. Okay. This is fine. We are fine now with the numbers? Okay. So the numbers now okay. Now the only thing that it's important that it's in our box, we have mu. We have some constant, okay, so we have n average divided by v to the power 2/3, and we have everything else, which is 3 pi squared to the power of 2/3, h bar divided by 2m, etc., etc. Now, this quantity, yeah, so this quantity, this guy, so it's the density of the electrons in a metal. It is of the order of 10 to the power 22 to 10 to the power 23. Okay, huge number of electrons. Okay, this number, okay, is also a given very specific number. We have only constants, we have h bar, we have the mass of the electron. Eventually, if we put down all those numbers, we obtain that mu of this free electron gas is of the order of k Boltzmann multiplied by 10 to the 3. Okay, I'm 10 to the 4, I'm sorry, 10 to the 4. Okay, so it's of the order of 10,000 k Boltzmann. This is our Fermi energy. Okay, so the Fermi energy is huge, is extremely large for this electron gas. Is it good or is it bad? Well, it is what it is, first of all. But second of all, we can then ask ourselves, well, remember this probability, occupation probability that we used? Okay, so the occupation probability, F, as a function of epsilon divided by mu, looked like something like this. Okay? And how smooth the function is was dependent of what? Of mu divided by k Boltzmann T. Okay? Mu divided by k Boltzmann T. The larger this fraction was, the sharper this transition was too. Okay? Moreover, we also said this is exactly 1, this is exactly 1/2, that only a small vicinity around mu, the only small portion of those energies around mu, they're contributing to the behavior. All the states that are over here are constantly occupied. All states that are over here are constantly occupied. We don't care about them. Now, what we get from our model? We get from our model that if we have free electrons, okay, free electrons, what happens? Mu, the energy of the electrons that are contributing something, is extremely high. Okay, is 10,000 Kelboltzmann. So let's assume that we are looking on the system, okay, not in the very low temperatures, but actually in room temperature. Okay, I want to look on the system in a room temperature. In a room temperature, K Boltzmann T, it's around 200 K Boltzmanns. Okay, mu is 10 to the 4th K Boltzmann, or is actually maybe 10 to the 5 K Boltzmann. Basically, this fraction in a room temperature is of order 100. From 100 to 1000. It basically says that the energy of the electrons that are doing something and not simply constantly occupying the states is extremely high. Is much higher than the room temperature. Is much higher than the average kinetic energy. What it means? It means that the only electrons that are going to do something have extremely high kinetic energy. Okay? Now let's assume, I told you that this model is extremely good. Why it's extremely good? Because let's assume that we had some sort of interactions between the different electrons. Coulomb interactions or some other kind of interactions. What will happen? So this interaction will spread a little bit the different energies of the different electrons. Okay? But it's only going to push the spectrum a little bit more to the right. Okay? So all the electrons that are going to participate are still going to sit around this free energy, around this mu. Now, if this mu is extremely large, we don't care about interactions. The electrons that are doing something are extremely hot electrons. We can say that their effective temperature is 10,000, okay, when the room temperature is around 200, okay, Kelvin. They don't care about potential energy. They only care about their kinetic energy. Now this is why this model works extremely good in room temperatures, because in room temperatures we can completely neglect interactions of the different electrons. Why? The interactions, okay, are going to be important somewhere over here for those states. Okay? For extremely high energies electrons, the interactions are not important. The only thing that is important is the energy of this electron, and the main contribution comes not from the interaction, but it comes from the kinetic part. Okay? So what we can now state is the electrons that are doing something, for us doing something, participating in conduction, okay, are only electrons that are near the Fermi energy. The Fermi energy is extremely large, so their kinetic energy of those electrons is extremely large. Do they have some additional Coulomb interactions? It doesn't matter. It's not going to contribute 10,000 K Boltzmanns. It's going to contribute 1 K Boltzmann, 2, 3, 4, 5, 10 K Boltzmann, something like that. Not much more than that. So the only thing that's important is the kinetic energy. And if it's the only thing that is important is kinetic energy, they are simply free electrons. Okay? So to sum up this model, we looked on the free electron gas, and we obtained that the Fermi level, okay, the Fermi level is very high. Why it's high? Why it's extremely high? Because we have a lot of electrons. If we have a lot of electrons, they cannot all sit together somewhere down there in the very low energies. They pile up. Okay? They pile up in the energy spectrum. So some are sitting in very low energies, and there are more and more and more and more and more. The electron cannot penetrate to very low energy because it's constantly occupied. Okay? So we're looking on somewhere up there on energies which are only kinetic energies of the electrons, which are extremely high. Any additional potential contribution or contribution of the potential energy is negligible. We can neglect it, kick it out, and use systems which are, we can say, well, they are interacting, okay, but because of the quantum nature of those particles, we say this interaction is not important, even if we are in a very low temperatures. Why? Because the nature of these interactions or quantum interactions eventually builds up extremely high Fermi level, and this Fermi level says everything that's over here, it's not important. Only this region is important, and in this region the kinetic energy enslaves the potential energy, and it's simply a system of free electrons. What we are going to do, not today because it's already too late, but next week, because Tuesday we don't have a lesson, so next week we are going to learn about Bose gas and Bose condensation. See you next week.